Hello, good morning, sir.
Good morning.
Sir, can we wait for 5 minutes to
Sure,
begin the
sure,
session?
sure, sure,
Oh,
sure.
may we start, sir?
Sure. Is it visible, my screen?
Yes, sir, it is visible. Kindly allow me to give the introduction, sir, and start the
Sure,
session.
sure, sure, sure.
Okay. Good morning, everyone. We have Dr. Zamir Ahmad Wani, sir, as our today's speaker. It gives me immense pleasure to introduce Dr. Zamir Ahmad Wani, sir. The sir is an eminent academician and researcher currently working as assistant professor in University of Kashmir. Sir research area covers a wide range of domains including antenna designs, metamaterials and metasurfaces, RIS, millimeter and terahertz communication. Dr. Vani sir has published extensively in reputedly international journals and conferences and has guided several research projects focused on next generation wireless system and AI driven communication technologies. Now, we warmly welcome Dr. Vani Ahmed sir and request you to kindly begin with the session. Thank you very much, sir, for accepting the invitation, and we request you to kindly take over the session, sir.
Thank you very much for the introduction. So I'm, as the uh, has been already introduced, I'm Zamir Ahmadwani. I'm currently working as an assistant professor at the Department of Electronics and Instrumentation Technology, University of Kashmir. And my research is mostly focused on millimeter wave antennas, which I had done in the last 5 to 6 years, designing millimeter wave 5 antennas for 5G communication using metamaterials and metasurfaces. How these metamaterials and metasurfaces they enhance the radiation properties or increase the antenna performance for millimeter wave 5G communication. So this will be the outline of my presentation. So we will first introduce what are the requirements for millimeter wave communication and how to design such antennas because at millimeter wave frequencies we have frequencies that are beyond this RF and microwave communication, and what are the different propagation issues that are there that we are going to first address and see what are the issues and how do we design these antennas for such millimeter wave communication systems. So then we will see different kind of antenna topologies which addresses the issues at millimeter wave communication, such as wide scan antenna arrays. Then we have multi-beam antennas for increasing the SNR at millimeter wave communication. Then we will see lens antennas which help in reduce the system complexity in case of phased arrays antennas. We will be addressing the system complexity and uh, design issues by proposing these lens antennas, which are uh, kind of simpler in design and does not have much issues at millimeter wave communication. Then we'll see multi-beam and quad beam antennas at millimeter wave 28 gigahertz frequency band. So the 28 gigahertz band, which was proposed for millimeter wave 5G communication in a couple of countries, US and Europe, but in India it is around 26 gigahertz of band was allocated for millimeter wave 5G communication. And before setting up a communication system at such high frequencies, or 28 or 26 or 35 gigahertz frequency band, what are the issues? For example, there is an issue of path loss because if there is an antenna, it is radiating this electromagnetic waves. So considering it is an isotropic source, so it will be radiating in all the directions, and the radiation it will decrease as 1/r² if we go to some certain distance. So the radiated power it will decrease as the distance increases from transmitter and receiver. So the loss that are associated with this path loss, or if we compare the path loss, this path loss, which is the spreading of these wavefront in spherical fashion, because antenna will be radiating in spherical fashion, spherical wavefront. So the power will decrease, and how much the power will decrease at 28 gigahertz band, you can see from the figure, from the table. So with respect to frequency, for example, 2.4 gigahertz frequency, we have a path loss of at an distance of 10 meters is around 60 dB, but at 28 gigahertz, it is 81 dB. So that means 20 dBs of more loss is there at 28 gigahertz frequency band as compared to conventional 2.4 gigahertz. There are issues like blockage. Blockage is one of the main issues at millimeter wave frequency band. For example, tinted glass. If you have a tinted glass, the loss that is happened due to this glass at 28 gigahertz is around 40 dBs of loss is there as compared to bricks. If we see bricks, the transmission loss that will be of the order of 28 dBs. These were the measurements that were done by Professor Ted Rappaport, and he has reported in this reference mentioned below. And atmospheric absorption there at 28 gigahertz, it's not much. It's around 2 dBs or 1.2 dBs at 28 gigahertz band per 200 meters of distance. So the main issues is blockage, which is of the order of 40-30 dBs, and the path loss, which is around 20 dBs more as compared to conventional sub 6 gigahertz 5G communication. So since path loss is dependent on the are inversely proportional to the frequency square, or lambda, it is directly proportional to lambda square. But the gain of the antenna for the fixed aperture at these higher frequencies, if I have a same antenna at working at 2.4 gigahertz, or working at same antenna working at 28 gigahertz band with the same aperture, the gain at 28 gigahertz will be more, because the gain is inversely proportional to lambda square. So since the path losses will be more, but the gain of the antenna for the same aperture will be more. So we can compensate this path loss by having gain or higher gain of these antennas for this fixed aperture. For the same antenna size at 2.4 or at 28 gigahertz, we will be having much more gain as compared to 2.4 gigahertz. So which will eventually compensate the path loss that is there. So we can compensate the path loss. So path loss is not an issue at millimeter wave frequency band, but the blockage is. Blockage, if the signal is lost due to blockage, we cannot do anything. But path loss, we can increase, or we can have lower path loss if we have uh, highly directive antennas for communication. So this was reported in this publication by Professor Ted Rappaport. So he has done the channel measurements at 28 gigahertz around the New York city. So for an SNR of 10 dBs, for the signal to noise ratio of 10 dB, he has showed that how much distance that can be covered at 28 gigahertz frequency band by having these antennas transmitter and receiver gains of 10, 20, or 30 dBs. For example, here you can see that at uh, at a combined gain of 30 dBs, 15 dB of transmitter gain and 15 dBs of receiver gain, we can achieve a 100 meters of distance at 28 gigahertz with a 10 dB of SNR, which is quite good for these for demodulation or for recovering the message signal. So if we for different curves, these are n for different curves. These are path loss exponent, and n equal to 2 is for free space. If you have a free space, there is no obstruction between the transmitter and the receiver. But since the practical environment, it will have different obstructions between the transmitter. For example, buildings will be there, trees will be there. So this n is for obstructive environments. So for different obstructive environments, he has showed that we can achieve uh, 300 meters of coverage at 28 gigahertz band for 10 dBs of SNR for n equal to 4. And for n equal to for less obstructive, we can achieve much more distance at these frequencies. So he has shown that we can cover up to 300 meters using for this curve for n equal to 4 for obstructive environment, having buildings and objects in between transmitter and receiver. We can achieve beyond 300 meters of distance for an 10 dB SNR, which is same as cell size at sub 6 these frequency bands, or 3G and 4G cell size we have currently in the communication system. So we are sure that we can achieve this communication at 28 gigahertz as well. But if there is no blockage between the transmitter and if there is a blockage, then the signal will be lost, which is the main advantage. So these are the issues at millimeter wave frequency band. Issues is propagation loss is there, which is the path loss. Solution, we can design highly directional antennas which will compensate for the path loss that is there. But the highly directional antennas, they will suffer with coverage, because highly directional antennas, if there is a communication happening between the highly directional antennas, there will be line of sight communication. But if there is a misalignment between transmitter and receiver, the the reception of the signal will not be there, because if we have highly directional antenna, if there is a certain misalignment between transmitter and receiver, the signal reception will be lost. So coverage is the main issue which is happening with the highly directional antennas. Now, how do we address the coverage? Coverage can be addressed by having antennas with wide scan radiation patterns, or we can steer the radiation pattern over wide scan angles. If the signal is lost, we can steer the beam so that to adjust for any misalignment between the transmitter and receiver for line of sight or non-line of sight communication. But shadowing or blockage is the main issue at millimeter wave frequencies. So that can be addressed by having dual beam or multi beam antennas, because if we see in a MIMO communication system, so if if in case of diversity MIMO, we send multiple copies of antennas, multiple copies of signals through various channels. So if one of the channel is lost, so there is a probability that uh, another copies of the signal is received using multiple antennas or multiple channels. So by creating multiple channels or using MIMO antennas, we can address the issues of blockage and shadowing to some extent. So in case of MIMOs, the outage probability is defined by P is the probability of error or probability of not receiving the signal, or there's a probability that signal will be lost. P is that probability, and N power N and M. N is the number of MIMO antennas that is there. But if these MIMO antennas have M beams, each antenna have M beams, the probability of error will be significantly reduced. Probability outage probability will be significantly reduced if you use MIMO as well as multi-beam, each antenna having multiple irradiation beams, and then arraying those multi-beam antennas to have multi-beam antennas with MIMO. So outage probability can be because P is less than 1, the outage probability will be less than 1. So powered with N greater than 1 and M greater than 1, the outage probability can be significantly reduced if we have multi-beam antennas and in MIMO configuration. And the antennas that are currently used, or the communication that is happening at millimeter frequencies, it was earlier proposed that we will be using beamforming or phased arrays antennas for if there is a shadowing or a blockage, we can use these phased array antennas to steer the beam to a particular desired location. So, but the designing of these beam forming, hybrid beam forming, analog beam forming antennas at millimeter frequencies, they have an issue such as, because you have to design these phase shifters at 28 gigahertz frequency band, but designing of these phase shifters is quite tricky, and the amplitude of these phase shifters, we are not able to design the phase shifter with a stable amplitude at these frequencies with a large phase delays. So the designing and the system complexity is there in designing these beamforming antennas. So this issue can be addressed by having lens antennas with antenna arrays at the focal plane, which steer the beam to desired location by powering up an antenna at the focus plane. We'll be seeing those antennas. So in order to increase the gain of antennas, so what we did in earlier in around 2018, 2017. So for example, designing a dipole antenna at 28 gigahertz band, dipole antenna has a wide impedance bandwidth, so it covers the 28 gigahertz band. But the gain of this dipole antenna at 28, it's around 5 to 6 dB. But that is not sufficient enough for compensating the path loss at millimeter wave frequencies. So what we did, we integrated these capacitively loaded unit cells. So these actually increase the refractive index of the media by printing these CLL arrays on the in front of these dipole antenna. It actually increase the effective refractive index of the because dipole antenna, it will be radiating, it will having x polarized radiation. That means electric field will be in x direction. This is the x direction, and by having these kind of capacitive loaded cells, the effective refractive index can be increased by arraying these. Thereby, the radiation that is emitted by this dipole antenna will be focused along this region only, because it will be having high refractive index as compared to the substrate. So effective refractive index will be increased, which will try to focus the radiated field along this. It will work as an directors to this dipole antenna. But we have compared with the Yagi-Uda configuration as well. So we saw that by arraying these CLL arrays, it actually increases the refractive index of the antenna and have a higher gain as compared to Yagi-Uda configuration for the same size. So this is the phase profile of the radiated field. So you can see that this is without printing these CLL arrays in front of the dipole antenna. So the blue curve is with this printing of CLL arrays in front of the dipole antenna. This is the phase profile that were plotted along this line. So we see that the phase of the radiated field, it becomes flat. If the phase of the radiated field becomes flat, that means the gain is increased because the power flows perpendicular to the phase profile. So for example, in this red curve, the power flows in all the directions. That's why the gain is reduced. Gain is around 5 dB because the power flows perpendicular to the phase profile. So by arraying these highly refractive index unit cells, the phase becomes flat. The phase profile of the becomes flat because all the fields that are coupling from the antenna uh, are leaving the this highly refractive index surface at the same instant, same time. Thereby, the phase profile becomes flat and the gain becomes more. So the radiation is happening only in this direction. While as in case of without the arrays, the power flows in all the direction. That's why the gain is reduced. So we increase the gain by printing this arrays. The phase profile becomes flat. All the fields that are exiting from this media are exiting at the same time, thereby increasing the gain. So these were the further studies that were done in this CLL array. So we have a radiated electric field without this printing of this array. The phase profile or the electric field that are emitting from this dipole antenna, it is going in all the directions. It is kind of an quasi spherical wavefront. While in case by arraying these, the phase profile or the electric field becomes perpendicular or the planar, thereby the radiation is happening in the z direction only. So this was the gain that were measured and simulated, and we saw that around 5 dBs of gain were increased from 6 to 11 dBs of gain were achieved. This gray curve is without these printing of CLL arrays, and this is E-plane radiation pattern of the antenna. Now, since the arraying of these or printing of these CLL arrays, it enhances the refractive index of the media on this region. So by if we print at an offset location from the dipole antenna, what will be happening? The radiated fields that will be coupling to this CLL array will be traveling with lower phase velocity as compared to the fields that are exiting from this without this CLL array. So there will be a phase difference between the radiated fields on one side and the other side. So the radiated fields that are going from the left are going through the substrate and the air, so they'll be traveling faster as compared to the fields that are going through this substrate printed with CLL arrays. So there will be bending of the waves because these waves that will be exiting much later than the waves that will be going from this left hand side. So there will be kind of a bending of the radiation that will be there. And this is the mechanism. So this green is the refractive index of the media with CLL arrays. This is the substrate refractive index. So the waves going through the substrate and waves going through this media, uh, through this LM or the media, will be traveling much slower as compared to the substrate waves. So they will be bending towards the right. So that will be calculated using this formula. So for offset of 6.32 millimeters, if we are offsetting this array or printing this array on the right hand side, the radiation will be tilted towards 24 degree, and which was verified using simulations as well as in measurements as well. So this is the radiation pattern or E-plane radiation pattern of the antenna with CLL arrays for different offset positions. For offset along right plus 2.32, minus 6 point on the left 6.32, plus 6.32 and plus 6.32. These were the measured. So we can further see the bending of these waves by plotting the phase profile of the radiated electric fields. This is the phase profile, and this is the magnitude plot of the radiated electric field for offset of 2.32 and offset of 6.32. So we see for lower offsets, the peak is happening at around 1 millimeters, and for an offset of 6.32, the peak is happening at around this 5 millimeters. So there will be the uh, radiated fields are peaking at different locations depending upon the this offset, and the phase profile for different offset positions is given by. So for more offset position, the phase profile is bended towards the right, and that is why the power will be flowing along this direction. So there will be bending towards the right. So this concept was then used in case of these three antenna element arrays for having bending as well as enhanced increased gain for the three antennas with 64 degrees of beam coverage. So there will be three antennas. All three antennas will be firing up these high refractive index surface. So bending will be happen for this wave. For A1, the bending will be towards the right. For A3, the bending will be towards the left, and A2 will be firing towards this Y direction. So there will be three radiation patterns for the three antennas, and this each antenna element does not interfere, or there is an isolation between these antennas. This is 60 degrees of isolation between the three antennas. So these were the measured results. So three antennas having three radiation beams. One is 60, 90, and 120 degrees with a coverage of non-overlapping coverage of 64 degrees were achieved using this configuration. So this antenna can be used if we have if there's a line of sight communication between this central element, and if there is a misalignment, we can fire up any of the two antennas so that to make up the communication between the transmitter and the receiver. So these are the comparison of existing literature as well. So this now the beam tilting, like we saw in earlier this antenna, the beam tilting were fixed. We have an array of these CLL arrays that is printing at an offset direction, offset position, and we get an beam tilting towards the CLL array. However, the beam tilting was fixed. We cannot control the beam tilting angle. But in case of if you want to control the beam tilting angle theta s, we can design these kind of an meta surface. It's an 1D meta surface. So there will be an array of meta surfaces which will be having a transmission phase which can be steered or which can be changed by changing the dimension of this unit cell. So this is an unit cell. This is an array of two unit cells having a transmission at 28 gigahertz band. Transmission is close to 1 for this unit cell, but the phase gradient is there. So this is the S21 phase that is plotted with respect to frequency. So this was designed at 28 gigahertz band. You can see for different A's, for different uh, dimension or length of this square A, one side of A. So we can have different phase, transmission phase of the unit cell. So for A equal to 2.9, we have a phase of around at 20, we have phase of around 150, close to 100. And for changing the dimension to 2.82, we will having a phase of 400. So there will be a, we can steer the phase from 0 to 360, or phase difference between the different unit cells can be achieved. So these were then arrayed in the 1D fashion. So, and along the x direction, there will be a progressive phase delay between the unit cells. So, for example, this gives a phase delay of 0, then this will be giving a delta phi, 2 delta phi, 3 delta phi, 4 delta phi, 5 delta phi. And using an array theory, because if we are firing these unit cells metasurface from one side using a plane wave, so if we are firing it with a plane wave, the radiation on the other side will be focused at a single point, because if there will be an sorry, if we are firing at this location from one side using a plane wave, so the plane wave will be bent towards the right if there is a progressive phase delay between the unit cells on the right. If the unit cells that are positioned along the x-axis will have a progressive phase delay, the bending angle can be calculated, or the progressive phase delay can be given by this. This is used array theory concept, because these, if we are firing with a plane wave, these unit cells will behave as a secondary sources of radiation. So using a concept of array theory, we can design these unit cells with different delta phi's progressive delays, because these progressive delays delta phi's we can control by the dimension of a. So we can control delta phi by dimensions of the unit cell. So thereby, by controlling the delta phi, we can control delta theta s. Sorry, the bending angle, we can control that. So this was designed, and this was loaded to the dipole antenna with high reflecting like surfaces, which increase the gain. And eventually, if we are firing uh, this 1D metasurface using these high gain antennas. So radiation will be, if we have an 1D metasurface with a progressive delay along the x-axis, the radiation will be bended towards the x-axis. So we can confirm from the full wave simulations using a patch antenna in the 1D metasurface, the radiation was tilted towards the right. Similarly, if we load it to the this fabricated prototype, it was bending towards the right. There is a calculated theta s, or calculated beam tilting angle was around 25 degrees. We can increase the this beam tilting angle towards right or left by designing this delta phi, the progressive phase delay in x or minus x direction. This were the bending of these radiation using 1D metasurfaces. Now we can, in case of dual beam antenna, like we have seen in the earlier slides, in the introduction slides, that if we are having an MIMO antenna or a multi-beam antenna, the SNR that will be used, or the SNR will be increased if we have multi-beam antennas. For example, if you have a dual beam antenna at the receiver side, so if we are having a MIMO communication, and if you are using a dual beam antenna, what will be happening at the receiver side? We will be receiving power uh, from two locations, because multi-beam antenna or dual beam antenna will have a radiation pattern going into two directions. So at the receiver side, we can combine the received power to increase the signal to noise ratio at the receiver side. So designing dual beam antennas are actually crucial for millimeter wave frequency band, and it actually enhances the signal to noise ratio at the receiver side, and also decreases the outage probability. Like we said, that the outage probability is reduced if we have MIMO communication, as well as if the each antenna in the MIMO communication is multi-beam or dual beam. So the outage probability will be significantly reduced. And we designed these antennas with a dual beam antenna, a single antenna having dual beam radiation pattern. This was done using these anisotropic media. This is a single epsilon high anisotropic media. For example, we have an media which is an anisotropic. The permittivity tensor can be given by this. So there are three epsilons: epsilon x, epsilon y, and epsilon z. So if epsilon x is greater than the other two, so we call it as an anisotropic media. Single epsilon h, because one of the components of the epsilon along x direction is higher than the other two transverse axes. So epsilon x is greater than the other two. So for such media, if radiation going through this media, there will be TE or TM radiation that will be going through this media. The dispersion relation can be given by this. Red one is the transverse magnetic waves that are going through this media. For example, this green color is the this anisotropic media with epsilon x. The permittivity along the x direction is greater than the y direction. So the transverse electric fields, transverse magnetic fields, transverse magnetic field means magnetic field, the magnetic field will be along the hz direction, while as the electric field will be in this plane, yx plane. So the dispersion relation or the phase relationship for the propagation of these TM waves is given by this. These are the propagation vectors, phase propagation vectors kx along the x direction, and this is along the y direction, transverse direction. So for this TM waves, the phase relation is it's an ellipse. It's an equation of an ellipse. That means the waves that are going along the x direction, will have same phase profile, because the propagation vector, the waves that are going along the x direction will have same phase. All the waves that are going through this media will be having equal phase profile in the x direction. So if epsilon x is greater than, that means this ky or the transverse component of propagation will be smaller as compared to other. So the propagation will be happening in the x direction. So the waves that are going through this media will be bended towards x direction. So this was then verified using FDTD simulations. This n is the effective refractive index if there is an anisotropic media, and there are two permittivities along x and y direction. So the effective refractive index is given by this, and this is the plot of the effective refractive index for different refraction angles inside this anisotropic media. And using these FDT simulation, we see that if epsilon x and epsilon y are equal, then the bending will not be much. But if epsilon x is greater than the epsilon y, bending is towards the x-axis. So we can bend the waves or bend the radiation inside this anisotropic media towards the optical axis or towards the axis which is having higher permittivity. So this concept was used to separate the radiation from the dipole antenna. So this is the this is the concept of generating dual beam radiation from a single source. For example, it's a single source which is loaded in FDTD simulations using this anisotropic media having epsilon x 10, then and epsilon y and epsilon z close to 1. So epsilon x was given or defined in the FDT simulation as 10, and as compared to y and z direction, which was 1 and 1. So we see that the radiation that is emitted from this Gaussian source, the radiation inside this anisotropic media are bended towards the x-axis, the optical axis, and thereby exiting the media at different locations. So separating the radiation from this source. So this was then verified using full wave EM simulation in CST Microwave Studio. So we had this dipole antenna in simulation. Then we defined this user defined media with epsilon x close to 10 and epsilon y and epsilon z close to 1. So this was then loaded to a dipole antenna, and we see the radiation or the emitted waves that are from the dipole antenna are traveling inside this media that are bended towards x direction along this direction and this media, and exiting the this user-defined media at different locations, thereby generating two radiation beams from a single dipole antenna. So this was then verified using these full wave simulation. We saw that two radiation beams that are generated from a single source. However, these were the user-defined media, because we have defined the media in the CST Micro Studio as a media, anisotropic media with epsilon x 10 and epsilon y and epsilon z close to 1. So now, in order to practically realize this media, we have to design this media using metamaterials. We design this using this kind of a unit cell, which is an anisotropic unit cell having epsilon x. This is the epsilon x along the x direction. We design this unit cell for having epsilon x close to 15 along the x direction, and along the y direction, because y direction is going electric field going into the plane of this or into the screen of this presentation. So there won't be any resonances that will be occurring due to the electric field along the y direction, which is perpendicular to this substrate. So the effective permittivity along the perpendicular direction will be same of the substrate, because there won't be any resonances that will be happening if we are having an electric field perpendicular to the surface. But along y direction, x direction, the electric field is actually the electric field along the x-axis will be coupling to this unit cells, or there will be gaps between the unit cells, so which will enhance the effective capacitance of this unit cell, which will eventually increase the effective refractive index along the x direction. So we saw that for a single unit cell, the effective refractive index along the x direction, or for the x polarized waves, was close to 15. Then if we are arraying these unit cells, 15 such unit cells, so we will be having a refractive index along the x direction has to be 8 or close to 9. So if we are arraying it with air gaps, the effective refractive index will be reduced from 15 to 9. So we achieved an refractive index at 28 gigahertz band using these are non-resonant unit cells. So using these unit cells, we achieved a refractive index close to 9 by arraying these 15 unit cells, 7 slabs with air gaps, 6 air gaps, that is 13 units configurations. And along this is the refractive index along this real part of epsilon along y is close to 1.48, sorry, is the which is the refractive index of the substrate. Whereas we have used a substrate of 2.2 Rogers 58880. So by arraying with it like this, these were then loaded to this dipole antenna like we did in the user defined simulations. So we had this 7 slabs. These are 7 slabs with 6 air gaps in between. So the total effective refracting, because one unit cell is having a refracting index along the x direction to be 15, but if we array these unit cells with air gaps, the effective refractive index will be reduced along the x-axis, and we got that to be around 9 along the x direction. Now the radiated fields used from this dipole antenna, that will be coupled to this media on the left and right. It will be guided along the x direction on both the axes. So they are exiting at different positions, thereby generating a dual beam radiation. And this was simulated in a major radiation pattern at 27, 28, 29, and 30 gigahertz, because we saw this is a non-resonant kind of unit cell. The refractive index is constant for this frequency band, 25 to 30. So we get this dual beam radiation. Now, since many people have designed these dual beam antennas or guiding of these unit cell using epsilon near zero or mu near zero metamaterial, but we have designed this using epsilon high media. So the flexibility is that in terms of this, we designed this using non-resonant unit cells because non-resonant unit cells are smaller than the operating frequency. So there will their size will be reduced, the effective size of the unit cell will be reduced. Also, if there is a change of that is happening of the effective refractive index in fabrication, so that won't much affect the effective refractive index of the media because if we have an epsilon near zero media and if there is a small variation in this designed epsilon, so the effective refractive index change in the effective refractive index will be more as compared to if we are designing high refractive index surfaces. Change in larger value of epsilon will not be much as compared to if we are designing using epsilon near zero or mu near zero medias. So these were then compared with other works. So we saw that our technique, it has good bandwidth in terms of radiation as well as impedance bandwidth. We have a dipole antenna, and then the radiation pattern was stable over the frequency band from 27 to 30 gigahertz. And if we have 7 slabs, and we can tune the bandwidth using number of slabs, because if we decrease the width of the media, the effective wavelength will be reduced. So this uh, we will have this radiation bandwidth. We can steer the radiation bandwidth from 25 to 30 gigahertz by adjusting the media height. So this is another technique of increasing. Now we'll see how to increase or enhance the gain of these antennas. First technique is very simple. This is an all substrate dielectric superstate that were enhanced to this dipole, this linearly polarized antenna. So if we have this kind of a substrate or dielectric, at the middle of this portion of this dielectric, there is no air gap in between the dielectrics, or there is a bulk of this dielectric that is loaded to the antenna, having an effective epsilon of 2.2. But if we have this air gaps in between the dielectrics, effective effective epsilon will be reduced because there will be air gaps using an effective media theory. So the effective refractive index will be reduced if we have air gaps in between the same dielectric. So how will be the if we considering this to be an isotropic antenna or an point source antenna? So it will be radiating in all the directions. The waves that are going through this lower refractive index or lower epsilon, lower permittivity media will have this will be having larger path length because they will be traveling to the farther locations of the substrate. So the effective path length can be adjusted by lower refractive index because the waves that will be going through this will have faster phase velocity as compared to the waves going through the central. But the central, this waves will be having smaller path length. So the larger path lengths are compensated by the lower refractive index or the higher phase velocity. Thereby, all the waves that will be exiting through the surface will be exiting at the same point, thereby increasing the gain of the antenna. So this is one of the simplest technique of increasing the gain, or this is kind of an flat lens. Like in case of dielectric lens, the curvature of the lens compensates the effective path length, while in case of this kind of an planar or dielectric lens, the effective, the larger path lengths are compensated by smaller this refractive index or smaller permittivity. As per this Maxwell Garnett theory, this is the effective media theory. If we are arraying these media or dielectric substrate with air gap, the effective refractive index will be reduced. Like This is the epsilon for a substrate, which is around 2.2 for substrate. If we are arraying 8 substrates with same thickness air gaps, the effective refractive index will be reduced. It will be reduced effective, this permittivity will be reduced to 1.5. So we can reduce the effective refractive index by arraying these air gaps, which will then compensate the larger path lengths to have equal phase profile on the top of this lens, which will then increase the gain. So this was then loaded to this patch antenna having these substrates. These are 2.2 permittivity substrates, and on the edges of the substrate there are air gaps in between, and the middle there isn't any air gap between the two, between the substrates. So, and we saw that the gain is then enhanced. This is a gain of a patch antenna. So this is with this dielectric stacking with air gaps on the edges. So the gain is enhanced. This was verified using measurements as well. So the technique of gain enhancement, it increases the flat phase profile is achieved for the electric fields, because this green is this blue is with this superstate, and this is without superstate. We saw that the change of phase that is happening from this 100 degrees of phase, while as in case of this without superstate, there is a phase change of 140 degrees. That means it is radiating in all the directions, while as it is concentrating the radiation to this planar profile as well, thereby increasing the gain. So, so this was one of the techniques of enhancing the gain of a patch antenna. So there is another technique of increasing the gain of an antenna by using these anisotropic lens. The lens, it works on the theory of guiding of electromagnetic waves along the optical direction, like we did in the dual beam radiation. For example, if we have a media having anisotropicity in it, and if we have an bipolarized radiation beam, bipolarized radiation source, that is, and considering that Ey, epsilon y is greater than epsilon x and epsilon z, so the TM waves, the radiated TM waves in the YZ plane, the TM waves, because waves can be, the radiation inside this media can be considered as TM or TE wave, depending upon which radiated source is firing these medias. For example, TM waves inside this YZ media, because magnetic field will be along the x direction. So electric field will be in this plane, YZ plane for TM waves. So TM waves, the dispersion relation can be written like this. And if we have Ey, epsilon y greater than epsilon z, we see that the propagation or the effective, the total k vector, if we plot the total k vector for TM waves, the total k vector, normalized k vector, will be for different for different thetas, the angle from this normal for different propagation paths inside this media will have this kind of an this normalized propagation vector, total propagation vector. Using this equation, we can plot total k, which is ky plus kz inside this TM waves. We can plot the normalized this for epsilon y equal to 10 and epsilon z close to 1. We can plot this total k vector with respect to the propagation angle or the oblique angle inside this media. And for larger angles, we see the total k vector is decreased. Total k vector decreases as we have oblique paths towards the y-axis. And we see that if we have an oblique path, theta is increased. If theta is increased, that means the path of the wave will be more inside this anisotropic media, but the total k vector is smaller. So path length is larger, but the propagation vector is smaller. So it what it does that the larger path lengths are compensated by smaller these k vectors, thereby the uh, thereby the phase accumulation along the y-axis in this case will be smaller. That means the waves that will be exiting this media will be with equal phase along the y direction. So if there's an equal phase exiting of the waves from this along the y direction, so the gain will be increased. So this was verified using full wave EM simulation by having this user-defined media with epsilon y 10 for different values of epsilon y. We see that if we are firing this media or if we are exciting this media from the bottom using a plane wave, we see the focusing of the plane wave to a small stress point. That means this slab, it acts as a lens. If we are exciting on the one side with an this plane wave, the there you see the focusing of this lens on the other side. So this is a property of a lens. So it signifies the lensing effect of this slab with epsilon y greater than epsilon z and epsilon x for this kind of an propagation along x, z and y, z direction. We see that if we are exciting with the plane wave on one side, there will be a focusing of the radiation that will be happening. And we have plotted the at the focal plane on this axis, we have plotted the power of the focusing for different values of y-axis along the y direction. We plotted this for different values of epsilon y, and we saw that for epsilon y equal to 10, for which we have designed this thickness, so we will be having higher focusing along the this y equal to 0 along the center uh, on the y-axis. There will be focusing of the power that will be happening for epsilon y equal to 10, and this signifies the lensing property of this wave because the larger path lengths were compensating by the smaller k vector. So the waves that will be exiting will have equal phase, so there will be increasing the gain. So and vice versa, if we are exciting with a plane wave, it will be focused on the other side. So this was achieved, and this was then loaded in simulations on a patch antenna with epsilon y, uh, which is the polarization of the patch antenna. Epsilon y was greater than other two axes, it was close to 10. And we see that by loading this anisotropic media, the gain of the patch antenna were increased to 14 dBi as against 7.4 dBi without this. And now this user defined, we have to realize this using practical realization. We designed this kind of an ELC unit cell, which was having anisotropic properties. For epsilon y, we choose the higher refractive index along the epsilon y as compared to epsilon x. So we see that by arraying these slabs, we tuned the effective refractive index for the media to be around 10, close to at this solid blue line is the stacking of these 7 ELC slabs. So we have achieved a flat this epsilon y of close to 10. Then arraying these 7 slabs and then loading to a patch antenna. This was then loaded to a patch antenna, and we see that there is no effect on the this impedance bandwidth because the thickness of the media, it defines the impedance of this uh, media, and we choose that to be multiples of lambda by 2. So it then signifies the reflectionless media of this reflectionless property of this media if we choose the thickness of the media at 28 gigahertz to be multiples of lambda by 2. So we had chosen this thickness of the media to be multiples of lambda by 2 at 28 gigahertz. And then we saw the radiation characteristics. This was HLE slabs, this was user-defined media, and this was the metamaterial lens that were designed. And we saw the user-defined media that were used in the simulations. Is the metamaterial lens is behaving similarly as to the user-defined media that we did in the simulations. So it exactly mimicked the this HLE slab to increase the gain of the antenna, and was then measured, and we saw that there is enhancement to a gain of around 13.8 dBi as against 7 dBi of the patch antenna. And these are the radiation patterns. And the aperture efficiency for this lens was close to 99% because uh, the aperture efficiency, the uh, aperture having a flat phase profile at each location, it signifies the aperture efficiency of the antenna. If you have a flat phase profile uh, on an surface, that will signify it is this aperture efficiency. Like all the aperture were having a flat phase profile. So thereby the aperture efficiency was close to 100%. So these were then loaded to another antenna, which was aperture coupled antenna, which is having some sort of bandwidth around because this patch antenna was having around 800 megahertz of bandwidth. If we want to extend the bandwidth of the antenna and see the radiation characteristics with the larger bandwidth, we designed this aperture coupled patch antenna, and same lens was loaded to aperture coupling. We see the radiation as well, and there were the radiation were fixed over the bandwidth, and gain was increased from this 27.5 to 29 gigahertz. So these were the high gain antennas. Now we will see the how to design these lens. There are two techniques to design a lens. One is phase gradient metasurface, or there is another technique of in designing this flat planar surfaces or planar metasurfaces for lens, or gradient index metasurfaces. So first we will see phase gradient metasurfaces. Phase gradient metasurfaces are metasurfaces where the unit cells, where the phase at each location or can be steered, or transmission phase can be controlled. So we can have different transmission phase at each location, which will be compensating the larger path length, thereby having this equal phase profile. So this was the one of the unit cells which we have designed. This is a transmission type of a unit cell, and 260 degrees of phase coverage were achieved by having this G. By steering this G, we can have this 260 degrees of phase coverage can be achieved. The transmission coefficient of close to 1. The lensing property of this lens, it was studied in EM simulation. We have excited with the plane way, and we saw the focusing on the other side. And we saw with different angles of this excitation of plane wave, the focusing is happening at different locations, which signifies the lensing property of this metasurface. This equation were used to design the this phase profile on the surface for the lens. This unit cell, it has a flexibility to have variation from 0 to 260. Ideally it should be from 0 to 360. Then we have quantized the phase to some extent to adjust the phase in this variation 0 to 260. And we have then loaded this lens antenna in this antenna array, which is an aperture coupled antenna array. So we saw that lensing property is happening. We saw that radiation for different angles, exciting 3 radiation beams at minus 15, 0, and plus 15 were achieved using this prototype. And this was the peak gain of 20.2 dBi were achieved, which amounts to aperture efficiency of 24.7%. So the aperture efficiency was not much because these were the resonant type of unit cell. The size of the unit cell was close to lambda by 2 for steering the these radiation for steering of this phase from 0 to 60. Because these are the resonant type of unit cells having a transmission coefficient at the design frequency. So that's why the aperture efficiency is not much. So this is a comparison of this work with different existing state of art. And then there is another technique of designing these lens antennas, and this is the graded index lens that we have designed. In case of graded index lens, what we do, we plot the this refractive index, or we normalize the we compensate the larger path lengths with the smaller refractive indexes. On the outer axis, the refractive index of the unit cell will be smaller as compared to the central element, because central element having will be fired with the if we are firing with the antenna at the focal plane, the path length of the radiation that is going from the focal plane to this central element will be smaller, so we have to give the extra phase delay, or we have to decrease the phase velocity in order to make the phase profile flat on this surface to have the lensing action. So this was done using this non-resonant type of a unit cell. The refractive index was changed, or we can achieve different refractive index by changing the length of this metal pad. So the refractive index variation from 1.4 to 4 were achieved by using this unit cell. Uh, we can steer the refractive index from 1.4 to 4 using this unit cell. While as in case of this from for the refractive index variation from 1.4 to 1 were achieved by drilling the holes inside the substrate of different radii. If we drill the holes if we drill the holes in the substrate, we'll be achieving a refractive index close to 1. If there is no substrate in between, so refractive index will be close to 1. While as in the central axis, there will be a refractive index which will be 4. Then 4, it will be decreased in this fashion using governed by this equation. So this was then loaded to an antenna array, 3-patch antenna array. It was then loaded a 3-patch antenna array, because the thickness of the thickness of the lens T, it also defines the focal length of this plane lens. So T was chosen to be 2 millimeters. Then we have stacked around 2.5 the substrates. We have we have stacked these 8 substrates with same refractive index variation or same unit cell pattern, and these were the holes that were drilled in the substrate in order to achieve a refractive index close to 1 on the outer axis. So we have then loaded to this patch antenna array, and we saw the gain was around 15 dBs for this smaller lens size. And we saw the aperture efficiency close to 50%, because the unit cells that were used were non-resonant kind of unit cells. These were smaller than the lambda by 2 that were used in the phase linear metasurfaces. So that's why the aperture efficiency is more in case of this. And these are the radiation patterns for three antennas, firing 3 antennas. Recently, I have worked on these multi-beam antennas, generating radiation beams or chord beam radiation beams using these anisotropic media. So, like we have already seen that if you have a media with anisotropic properties, there will be a bending of the waves that will be happening along the larger refractive index direction. So, the electric field EY and EZ inside this media, if there is an if there is an Y polarized EM source that is firing this media, stacked media on these two directions. So EY, if NY is greater than NZ, if we choose the refractive index along Y direction to be greater than Z direction, then the EY will be smaller as compared to EZ. The electric field will be smaller as compared to EZ. So the bending of the waves will be along the this Y direction. NY is greater than NZ, so EY will be less than EZ. EY will be less than EZ. So there will be bending of waves on these two directions, Y direction. So we will see an separation of the radiation from the patch antenna to have a dual beam radiation. So these were then checked in EM simulations. So this have resulted in a dual beam radiation by loading these anisotropic media. And this was the realization of this media using these unit cells. This is a unit cell, anisotropic unit cell, having NZ and NY greater than NZ. So this was then loaded a patch antenna. We saw the dual beam radiation that is resulted from loading these metasurfaces with different refractive index along Y and Z direction. So now, if if we are if we are loading this media along the polarization of this patch antenna, we will be separating the radiation into two directions. So thereby, we can achieve dual beam radiation. However, if there is an antenna which has polarization along both the directions, if we have a two-port antenna, both having polarization along y and x direction, we can separate the polarization of the electric fields, or we can achieve the dual beam radiation along the polarization of the electric field. So thereby generating chord beam radiation. So this is the radiation pattern for one port, and this is the radiation pattern for the two ports. So for both these ports, we will be having dual beam radiation for the antenna if we are loading on both the directions of the polarization. So this was the two antennas with polarization along y and x direction. But if I have a single antenna, for example, a circularly polarized antenna or an 45 degrees elliptic, this rotated patch antenna. Rotated patch antenna will have polarization along x and y direction as well. So by loading this media along both these directions, result in the chord beam radiation from a single source. So these are the radiation pattern. These were the designed radiation from an CP antenna, which were radiating circularly polarized. Both the components of the electric field were there, x and y direction at 28 degrees. We saw that by loading in both these polarization, we are separating the radiation in four directions, thereby generating a chord beam radiation. Similarly, if we are having a rotated antenna field, it will be having the polarization along x and y direction because total electric field will be in the middle of this x-y direction. So they are having components along x and y direction as well. So thereby separating the radiation along x and y direction, resulting in chord beam radiation. This is the radiation pattern measured and simulated for the CP antenna with this anisotropic loading. Uh, this is XYZ plane and this is YZ plane. These are the simulated S parameters of the antenna. So this were the chord beam antenna that were generating using a CP antenna or rotated patch antenna. So this and I will briefly introduce these meta surfaces that were designed for millimeter 5G communication. These are quite popular today. So if you have an this meta surface, there is an active meta surface or RIS or intelligent reflective meta surface is there. So if there is a communication happening between a transmitter, base station, and the receiver, and there is a blockage that is between base station and a receiver, so communication will be blocked. So we can design this active meta surface, which will then uh, steer the beam to a desired user space. So this was designed using this pin diode. Meta surface is a dipole kind of a configuration at this 3.5 gigahertz. So we achieved this. This was done in simulation only. So we achieved a phase of 180 degrees, phase difference of 180 degrees for diode on and diode off, and we can quantize this phase on a plane for different this distribution for 30 degrees. This were designed or mapped phase pattern, quantized phase pattern. So we saw that with patch antenna with the radiation for one on and off of diodes, we can achieve plus 35 and minus 30 degrees of radiation that is there. So this summarizes the work that I have done on this metasurfaces, metamaterials for millimeter wave 5G communication. So if you have any question, you can ask. Thank you.
Participants, if you have any queries, you can ask. Hello.
Yes, you can mail me as well. So if you have any query, you can mail me or ask me any further clarification on the these antenna designs,
Okay, sir.
or read my work at these.
Sir, I think no queries are there. Hello. Hello. Sir, am I audible, Vani sir?
Yes, sir. Yes,
Okay.
yes.
So I think, sir, there are no queries at present. And
Okay.
we will also share the email ID to the participants. If they have any
Sure.
query, they can ask.
Sure.
And, sir, thank you very much. We from MNIT Jaipur, thank you very much for accepting the invitation. And this talk was very much useful for all the participants, sir. Thank you for sparing the time for this talk, sir.
Thank you. Thank you very much for inviting me. And it was pleasure to talk. Thank you.
Thank you very much, sir.
Thank you.